Hey there, let's move to the second tutorial, the double oblique step. So the case is this is a pure convection case that we also have analytical solutions you see here. So basically we have here scalar, no diffusion, that is entering here, and then when you do a sampling, you will get this analytical solution. So here 0, in this area 1, and then 0. So this case is a numerical schemes killer. Okay, and here we're going to see in practice all the numerical schemes that we can use to deal with the convective term. Okay, so just to show you a little bit also here what we're going to expect. So see that using different methods we have different solutions, and we're going to see here a little bit what is a TVD. Well, we're not going to go into the theory, you have it here. I'm just going to show you how to work it out, and then also working with upwind, linear upwind, see that comparison with these two cases are accurate, see that the upwind is highly dissipative. And what is important to know here that also is a source of confusion is that in OpenFOAM there are many methods implemented to deal with the convective term, but in reality you don't need to go through all of them. You just need to work with this example or some other example and understand a little bit the difference, but also to choose a set of methods to use. So is my advice, okay, there are more than 50 methods as I mentioned, but it's my advice just to limit yourselves to a few of them. So you should use upwind. Okay, upwind is first order accurate, will always give you a solution, but it's too dissipative. But you can use it to stabilize your solution or get fast initial conditions. Then you have this one, or this, the linear upwind and linear upwind V. This is the preferred numerical scheme, and this is the default choice in most commercial software. So this one together with a good method for the Laplacian terms as we did in the previous scheme is all you need. Okay, then we have the linear. The linear is very accurate, but it's unbounded. It is oscillatory, so in the case that you have a strong convection, that most of the case, it will give you problems. Then you have the limited linear, that is an improvement of the linear. Let's say that this is a linear bounded. It's something that you will use with less simulations, okay, to avoid numerical diffusion, dissipation. And this is interesting to tell that it's recommended to less, because unless you need to use low dissipative diffusive numerical schemes, and not all numerical methods are born to be used with less. With no problem you can use in a less linear way, but you will realize sooner or later that it's too diffusive, okay, and you're going to lose a lot of information. And then you need to choose a good TVD, okay. So there are many of them. My advice, just stick with the Van Leer or min-mat, okay, those work very well. And maybe something that is in OpenFOAM, you have the LUST, which is a blended between 70% linear and 25 linear upwind. Something that you can play around and play with this numerical scheme. But sometimes, again, I use this when I need low diffusion. There are many more things in OpenFOAM, but unless you are doing research, stick with these methods. And in commercial software, these are the options that you will have available. Maybe sometimes they will also expose to you the quick method and the muscle method, that also you have it here, but we don't need to use it. This is more than okay. So that being said, let's go into the tutorial. Okay, so if you go to your folder where you extract everything, goes here to the double oblique step. Okay, and here we're going to have 3 folders, okay, different meshes. So we have quad mesh, tree mesh, and poly mesh. So you can see the influence also of the numerical methods in each mesh. So in this case, let's go to the quad mesh, okay, the first one, and let's start there. So quad mesh. As usual, remember that you have this script to run everything automatically. So now we're going to focus here in Okay, so let me go here in fvSchemes. Okay, so see that we go to the numeric. So this is pure convection, but it is unsteady. So we are using the method Euler. Later we're going to dedicate a little bit more to numerical schemes on time, but Euler is a first order accurate. We have seen that first order accurate is a little bit diffusive, even in time can be diffusive, but as you get your CFL low, there's not much diffusion that you will add. In this case, the CFL is lowest below 1, so it's okay, we have good accuracy. Okay, so we have the gradient schemes, and then we are going to work it out also to see how to set up this one. Okay, so here when you use this keyword, you are enabled gradient limiters. Okay, in this lesson, the theory, you will see what we're talking about, but this is mainly to avoid oscillation. So to start this case, just let me disable the limiters and put Gauss linear, the method. So one on also here you have this dictionary, you have also the options available in OpenFOAM. I put it there, and here you have a few of the numerical methods or discretization schemes that you can use. And here, let's go and run here linear. So the setup that we're using is a very accurate setup, but it is oscillatory. Okay, so let's see what we have, and then we go for the relaxation schemes. We have seen how does it work. In this case, put it orthogonal because this is a 1D mesh. Okay, perfect mesh, so orthogonal is okay. But remember what I told you, that it's better to use limited 1 instead of putting orthogonal. Okay, it's the most general setup, so it's better to go here and put limited 1. Okay, and also here limited 1. So let me do this update there. So usually also when you see in the folders the file org means that is the original one. So if at any point you want to go back to your original dictionary, you have it there. Okay, so these are the setup. In SV solution, again, we know also that we have these actions to control the loop for those corrections. So here you see that as it is a perfect mesh, I don't need to put it to here. And see that, as I told you, I recommend you always to put here too. Okay. And then as the solutions keep running, maybe you can go back to 1, you can reduce it to 1, but always monitor the solution. And just let me comment this one. Okay, so let me run the case. So this is a very fast case. Okay, remember to load OpenFOAM. So I invite you just to play around with this case, with all options, and see the behavior, the outcome. But in general, your outcome will be Upwind. You will see that it's very diffusive. So basically, when you run Upwind, your outcome will be, let me go back here. So when we talk about diffusion, you will, in this case, under predicting everything, see that by as much as 20%. And then the linear, which is very accurate, you see here, is oscillatory. And then you have the TVD that removes those oscillations. So TVD in combination with a good gradient limiter, it will give you stability and accuracy. So this is what we are going to work it out here. So see here that we run the case, and we have these oscillations. Okay, this is something normal of the linear. Okay, in this case it converges, but there are some cases that it will diverge. Okay, so let's go, for instance, from the linear. Let me change. For instance, I know that we have a method here that probably is the most accurate of all the super B. Okay, this is a TVD method, very accurate, but it has problems that you need to use a small CFL numbers time step to get it working. Usually it tends to diverge if you use very large time steps. So see, okay, let's see what happened with this one, sampling, and see that now this one is properly. And it's not diverging, it is iterating, it is converging, but it's the wrong solution. So have to be careful, always analyze your solution. So what we can do to stabilize this one, so let's go back a few steps. So let me reduce first the time step. Usually in unsteady problems, it can be also a good solution, okay? If you have the good numerics and if you still divergence, then you can go and focus on the time step or on the relaxation factors. So in this case, I went back, I reduced the time step, but see that still we have the problem, okay? So let me stop it here. So let me add the relaxation factors, and now see that in this case, actually in the relaxation factor have the stabilizing effect. So we do the sampling and we get it right there, okay? So you can come here, play with all methods, and let me go back. Okay, so let me use this stamp. So sometimes I have some comments there. So this one super B should be unbounded according to that description. Let's see what happens. And if I go do the sampling. Okay, so it's very bounded, the solution. Okay, so probably soon here, maybe there is a little bit unboundedness here, but that can be controlled. So if I go here, okay, and instead of putting over, let me use backward. So see that it's a little bit unbounded. So when we talk about bounded quantities, that by definition, we know that your solution should be the maximum value is 1, and see that here it is exceeding a little bit that value. So that is an unbounded quantity. It might not be that much, okay, in this case, not that much, but when you're working large cases, that can accumulate and can give you problems that you should be very careful about that. So, and if we go here now, Nicholson, also this is a second order accurate method, but again also is unbounded. Okay, so if I go a pure Nicholson, let's see what we have. Very similar behavior. It's becoming a little bit unbounded there. So since that we can do to stabilize this one, and for instance, if I go back here to linear, okay, you will see, okay, let me rerun. Sampling. See that is very oscillatory, okay? So we have seen the effect of linear, it's very accurate, but it's oscillatory. And as you choose many of these methods, that all these that will come here, there will be very accurate, now entering the category of TVD schemes. But usually of all these, just limit to these three, min-mod, Van Leer, and maybe the one you can use the Super B. So now let me use the Van Leer. That probably is my preferred method. So if I go there, then sampling, see that it is a little bit more diffusive than the Super B, but it still is very accurate. And see that we don't have any more of those problems here that we were having previously, that it was becoming unbounded. Okay, so they have a very nice properties, the Van Leer. I really like that method. And then we have the min-mod, that probably also is a very good choice. It's more diffusive than all the previous TVD, but again, it's accurate, very stable method. You see here, so it's a little bit more sinusoidal, as you can see there. So again, just take this case, play around with everything, try to make solver diverge or see those oscillations, just to get a feeling how everything works. So now we go to the Upwind. Okay, so the Upwind, we know that it will always work. Okay, but the problem is highly diffusive. So if I go now do my sampling, see that is incredibly diffusive. It's too much diffusion that you are adding. So, and just to show you that, the fact that I told you that it will always run. So as you go here with a very large time step, that the previous cases were giving problems, or it was iterating, but the solution was very unbounded. Let's see what we have here when we do the sampling. See that it is working, okay? And probably contrary to what you might think, that okay, larger time step will be less accurate. Here it seems that it's getting more accurate, but this is accuracy is not due to it is working well. It's just that numerical diffusion that is accumulating. And here we have probably error canceling. We have some error somewhere that is canceling one error somewhere, and probably that is helping the solution to have a good agreement. So if I go here 0.5 extremely large time step, that it should conversion to iterations. Still, it is converging, it is working, but you should be careful of the solution. Again, this one you see that you have a good agreement, but maybe that error cancel. So as you go back to any of the other methods, so for instance, let me go min-mod. It is unlikely that you will get a good solution, okay, but let's see, who knows. Scalar transport, run there. Okay, so still a good solution. So the min-mod is stable, so let me go with the super B. Okay, it was working. Okay, so you have it there. So we have the correction, so you see that very accurate. So let me go here and let me increase this there, so to reduce that. So again, it's working, so we should have, okay, so see that kind of now very large time set. See that now clearly you see that unboundedness. So in this case, relaxation factors have a very important effect. So also you can get the feeling of the relaxation factor. We go now Van Leer. We do the sampling and see that oscillatory as well. And let me go, for instance, min-mod. We should have something similar. Okay, the min-mod is very stable. Okay, so I really like the min-mod. So let's check here the muscle skin. So this is a very interesting method because actually starts order accurate. So this is one that extra accuracy you can go. But again, don't use these methods. It's very rarely when these kind of methods are used. Okay, so production runs just stay linear wind and a good TVD skin like the min-mod of Van Leer. Okay, so again, this is oscillatory. So let's say that we have those oscillations. Okay, let me go back to the Van Leer that was oscillatory. And probably one way to erase those oscillations from the solution can be just going there and putting the famous gradient limiter that I will add here. So the default is one, so it's a cell-based method. You have the option also the Gauss no base reconstruction, and then you have the least square. Those are the most popular methods. Okay, all of them are second order accurate. Again, you can play with them, but I like pretty much to use this one. So limited Gauss linear one, it's very effective. And let's see what we have. So see that now you don't have the oscillation. There is some diffusion. It's not very nice solution, but we know that we play with that with the time step. So maybe as we reduce, we're going to get the better agreement. But the idea of that gradient limiter is just to when the gradients are being reconstructed, if the gradient is larger than the value of the neighbors, you will clip the solution to avoid that unboundedness. So that is the idea of the limiters. So let me go back here. It was 0.025. So if we run with that value, And probably here we should have a very nice reconstruction with the one layer. Okay. And then you have also more aggressive advanced, let's say, when you do the gradient limiters, the method used to limit is the min-mod, the default method, but also you have the options to change that min-mod. So see here that you have a qubit limiter or the Venkatakrishnan limiter, okay? So you can use it with the Gauss reconstruction, cell-based, node-based, or the least square. Okay, so usually this qubit, this is a very accurate one as well. Okay, usually this will be one when you have extreme severe case. Later we're going to see one of those cases, shock wave moving in a tube, and then you can put that one to get that extra accuracy. But it's a very good reconstruction. In this case, it might be difficult to see the difference, but it is very accurate, very stable. I really like this method. But as I mentioned, just stick with this one. This is my preferred one, probably the most accurate one, and also is a little bit less sensitive to skewness, is the least square. Okay, but sometimes I have found that it can be a little bit difficult to get a conversion tetra mesh, triangular mesh, low quality, tetra mesh with low quality. But in theory tells that this is a much better method. Also, you can use it. Okay, so again, my preferred way. So I start my simulation like this, and then I let it run. You monitor your residuals, everything, and at one point I go to least square. Okay, I know that one is more accurate, but I always let it go like this one because I know it's very stable. Okay, so you can go here least square. We won't see any difference here, maybe. Run sampling, and you have it there. Okay, so backward. So this setup that I'm showing here is a very accurate setup, but it's a little bit oscillatory because of this time. So maybe one recommendation here is just also go Krant-Nicholson and this blending coefficient, put it to 0.7, okay? That will help to stabilize your solution. Okay, I don't need this there. So we go this one. Okay, and as you put the coefficient to 0, it's equivalent to the Euler. So actually, this is my default option now, the Krant-Nicholson, because but you can play with this coefficient. Then gradient limiters. Okay, how you compute the limiter. So if you don't use this keyword or you put this coefficient to 0, you are switching off the limiter. So you put it to 1, it's always on. Okay, it's the most aggressive setup. And here you have the different combinations. Then when it comes to the divergence, the convective part, my advice always, this is very accurate. Okay, always stick with this one. And the linear wind, second order wind. But have in mind that you can have the wind, a good TVD, and a linear, then in this case it's a little bit unstable. One thing that the linear wind will ask how to compute the gradients. Okay, so this, you will use the definition that you have here. So here you will put grad t, how you compute it, and here it will compute in this way. Okay, so if you put default, it will take grad t as this one. If you want to explicitly define, you just add it here, grad t, and put whatever you want to use there. Okay, so let's run with this method. And voila. Okay, so we have a bounded solution, but let's say that this method have also, if I disable the limiter, I think, if I would recall, it might become a little bit unbounded. Let's see what happened. Okay, see that here is a little bit unbounded. Okay, so let's play around with time first. So let me go here. If I go 0 in time, and I plot it here, it's still it is unbounded. So it does not have an strong influence here, but in some cases it have an strong influence. By the way, you might ask, why is this so important to avoid these oscillations? First, look at that we have the analytical solution, so this is something that is not there. But then also imagine that you are simulating let's say a chemical reaction that you will have it when the temperature arrives to 1. So here you are artificially triggering something that is not there. So the whole simulation will be wrong. So that is why it's very important to have bounded quantities. Of course, also depends on the physics that you simulate, and sometimes this might be acceptable, you can live with this, sometimes it is unacceptable. Okay, usually I do external aerodynamics and I can live with this, but I need to keep it limited, and you should be aware that this might accumulate and this instability might grow and can make your simulation diverge. So how do we avoid using the linear wind grad T, the linear wind, how do we avoid those oscillations? We know that those oscillations, here the mesh is perfect, by the way. Everything is due to gradient reconstruction. So let's use, for instance, the least square method. Okay, so if I put here least squared with no limiter. Let's see if we have some improvement. So there is no apparent improvement. So let's add now this load limiter. So I will stick with the least square. By the way, you put it like this, always OpenFOAM will take the last one that you have in the list. And see, by simply adding that as load limiter, see that you have a strong influence in your solution. Now it's becoming very limited, your quantity. Okay, again, my default choice, as I mentioned, is this one, and you will see that it will have a similar effect. It's this one, my preferred one. But it's up to you. Again, play and find your method. But it's always recommended to use this load limiter. And actually, commercial software, they all use these load limiters, okay? And if you change this value 0.5, you are going to see that maybe it might start to become a little bit unbounded. So that is the quantity that you are limiting. So see that 0.5 is not okay. So this is important because there are some quantities that you don't want to limit too much. For instance, you're doing aerodynamic computations, probably it's not a good idea to limit too much pressure because it can have an influence on your forces. So usually in pressure, you try to avoid to add very aggressive limiter. And also, for instance, multi-phase flows also, you have the curvature of the interface. Also, you don't want to limit too much that quantity. But for velocity, it's recommended to be aggressive and limit that one. So let me go 0.9. Oops. Gosh. We do the sampling. And you see, we start to see that it's lower, but it's still, you have it there. So probably here in this case, we need to be very aggressive to avoid that unboundedness. So as we go now, should we solve the problem? Okay, so let me do also and see that now, if I go increase this to 0.5, still we should have something stable. Okay, now see that large times everything is becoming unbounded again. So at this point, I'm think that my problem might be now time. Okay, so let me reduce this one to 0 to default to enabler, and let's see if it has an effect here. So neither doesn't have a strong effect. Okay, so let me go with something more aggressive. That will be this one here. And let's see what happens. Okay, see that one is very aggressive. See that it reduced that one, but still there is something there that might not be ideal, but it managed to reduce that one. So again, play with these limiter actions. Okay, and let me go 0.7 here, put here 0.1. Also, you will have the options probably to under relax. So let me under relax. That probably it is a good solution in this case. I'll see that we have a perfect solution there. And so we play around in this case with divergence. Okay, this is the convective term, and we saw that you need to look all these options. So these are all the schemes that you have implemented there. So is the one is you're doing the theory, probably yes, you can look at that, but don't get lost there. But you need to know that you need to have to know that you can use the Upwind to stabilize the solution. Upwind always gives you a solution, but it's very diffusive, so it will highly underpredict or will predict your values. Linear Upwind probably is the best choice with a good grading limiter. Then we have linear that is very accurate, but it's oscillatory. And then you can choose a good TVD method. My choices is min mod of one layer. And then, well, I like to show Super V, that probably is the most accurate one. Okay, but you need to use as well. So stay with min mod or bond layer. And then you have many more methods. Okay, so this one I mentioned, you have the quid, the LUST, most of the schemes are this. Actually, these two are third order accurate, and quid also can be fourth order accurate in quad meshes. Okay, so we work it out here. Also, we work it out with the grading limiter. So you saw the influence of this there, and my advice also here is just to stick with this one and leave it always on. And then I like to use for time this. Okay, so I think at this point with tutorial 1 and 2 we address all the combinations that you have here. Okay, so we are ready to go to more advanced stuff. But what I want to show you also, we also saw the influence of the under relaxation. That will be the next tutorial. But now I want to show you that, let's move from this mesh. Actually, we didn't see the mesh. Let me show you the mesh. So in this case, it is a perfect mesh. Oh yeah, this is a, I forgot, this is a 2D. I mentioned one, this is actual 2D. It's a perfect mesh, okay? And what you have is the flow, your initialization, and then you convect it. And that's what you have, okay? So what is interesting, that let me rerun now, but just to show you what happens, that if I go and put it linear, okay, so let me run linear. Sampling. See that we have the fluctuations there, but if we visualize the solution, you will see that those are waves that propagate in the whole domain. So there you see that maybe it's not that much because we are sampling just in a line, okay? But when you visualize your solution, see that you have all these waves propagating that solution, and eventually that can make your solution diverge, okay? So see that you have many waves propagating in your domain. Okay, see that everything, even here that you have 0, see that is being propagated and it has an influence far where you shouldn't have anything. So those are the problems of the oscillations. And it will be the same effect where when you see some unboundedness, you will see that effect. When you visualize somewhere, you will see that you will have very large values or some wave propagating in your domain. Okay, so we work it out with this perfect mesh. Nothing to do there, but let's move now to a triangular mesh. Okay. So double oblique. Let me go here a minute just to fix something here. So the triangular mesh pretty much is the same idea. Okay, so basically what we have here is this. Okay, triangular, and we concentrated the triangles along the diagonal where we have the flow going. So let's see what happened here. Okay, so also we have solution here, and see that in this case, by using the limited Upwind, okay, the linear Upwind, see that is unbounded a little bit. Okay, so let's see this setup. Okay, so we have fvSchemes, fvSolutions, and control it. Okay, so we have our time step, we have the solution, so like the previous one. Okay, and then fvSchemes, and see that we already saw orthogonal there, that it might be the problem. Okay, and let's run this case. So go edge run all. So it will convert the mesh that was generating using something else, and then we are going to do the initialization. Okay, probably shows times a little bit too low, and I'm running for 2 seconds as well. And then we have the sampling. Okay, so we have this unboundedness there. Okay, so how can we fix that? So first, let me increase this one. Okay, so let me go there. So we go now fast and furious. Okay, so let's see what happened. Okay, still we have it there, but much faster. So the first things that we can do to avoid that, first, remember we have a triangular mesh, there we shouldn't use it, even though this is almost perfect. Okay, we shouldn't use orthogonal in these kinds of meshes. Okay, look at the mesh. So always remember this one. I think at this point this idea should be cemented in your brain. So it should be limited 1. Okay, and here also limited 1. Okay, so now let me rerun and let's see if it has an influence in your solution. So if I go and do my sampling, okay, doesn't seem to be, well, actually it won't have an influence because this is pure convection. Okay, so as you go into constant transfer property, see viscosity 0. Okay, but let's always remember that one, and actually here it didn't complain because you don't have that. So to avoid that problem, okay, so we can go and say, okay, let me use, for instance, you can say, okay, I will use Upwind. Okay, Upwind, it will always give you a solution, it will always give you a bounded solution. Okay, but this is not what we want. Okay, it's too much diffusion. So we can go, we have seen that the min mod is a good choice. If I put here min mod, let's see what happens now. We do the sampling and a nice agreement. Okay, so the min mod managed to solve without the need of adding that grading limiter. Okay, but sometimes you might need to add the grading limiter. So in this case, we have seen that using this one, our problem will be the grading limiter. In this case, we're added the grading limiter, but see this keyword there is multi-directional. So this is a selective limiter that you have. So usually when you add this limiter, that probably is the most diffusest one, it will limit all the gradients in all directions. Okay, so if you have one phase that is becoming unbounded, it will limit all other phases in the same way. Okay, so it will add some diffusion. This is something locally. In this case, this is kind of selective. So only the phase, only the direction that is becoming unlimited is becoming unbounded. So it's more accurate, but it might be a little bit more oscillatory. So that's why also I don't like to use that one. I prefer to use this one. Okay, so if we go and we put that one, we run, do the sampling. So see that the problem was solved just by having that limiter. Probably also you might play around with the under relaxation. It might have also an influence using this one. Okay, so as I go here, I use the multi-directional plus lower under relaxations, and it didn't have a large effect. Okay, so not always relying on the relaxation is a good choice. Okay, and okay, so we saw this, how it works, and see that even that we're using the Euler is also becoming unlimited. So this was for the tree mesh. Okay, so let's move to the other case that you have the poly mesh. Okay, so as you go to that directory, so this is what we have. Now we have a polyhedron meshes. Okay, so these meshes have very good properties. So you have seen that in the theory. As you go to a theory, you will see that to compute gradients depends on the fluxes across the faces. So in theory, the more faces you will have better gradients approximation. Okay, so that is the theory, and it might be true, but sometimes it can be a little bit tricky to get a stable solutions in polyhedron meshes. But these polyhedron meshes, general polyhedron, have good properties. So again, if we go here and let's open the basic dictionaries, this one and this one. So you see fvSchemes, you go fvSchemes, remember always, okay, instructor meshes, do not use that. Orthogonal, use limited one. Okay, in this case we won't have any influence because remember we viscosity, the diffusion is 0. Okay, limited 1, and then we have the same setup as previously. Okay, so check here also same setup as previously. So let's run. Okay, in this case again I left the time step, it's a little bit low, so you can increase it. And just a reminder also, remember that you have this grid and you have all the steps here. So here you can see that, well, I already converted the mesh to this format, but here also you have all the steps to get the mesh from Gmesh. Okay, and we're using this specific solver. Okay, so see that the polyhedron mesh actually got a good solution by using this limiter that in the triangular mesh it was a little bit oscillatory. So let's go and let me change this one also 0.1 here, 0.1 there, and let's rerun. So it's scalar transfer fun. Let's just run sampling. Okay, so I'll see that we increase the time step, no problem in the solution, it's still very bounded. Okay, so see also that here also see the influence that some meshes might have better approximations to fluxes and better computational gradients. In this case, the polyhedron mesh compute better those gradients. And actually the polyhedron mesh was derived from the triangular mesh, okay? So you get the triangular mesh, and using those triangles you reconstruct this polyhedron. So it was exactly the same mesh. Okay, so with this I end this tutorial. I hope you enjoy it, and again, just play around with the cases, and you see that they're very simple cases, but you can change many parameters. But the main takeaway here, do not get lost in all these methods that you have in OpenFOAM. Remember that you just need to play around within Upwind, linear Upwind, and a good TVD that can be the min mod of one layer. That's all that you need to know there. And also be careful with the gradients. That sometimes the gradients might be the problem, so you will need to bound that. So always leave the gradient limiter on. So that's all. Thank you very much for your attention, and see you in the next tutorial. Bye.